Our preceding lectures have been concerned with the subject of geometrical optics, which has been governed by the laws of reflection and refraction. Now we're turning to physical optics, and physical optics is going to include phenomena which can be explained by the classical wave theory of light. Over the next 3 lectures, we'll look at the phenomena of interference, diffraction, and resolution and image contrast. As we've seen, the large-scale optical effects can be explained by the use of light rays. However, the finer details require the wave picture, and that's what we're going to consider now. A lot of these details are only apparent when we look at the effects of light going through very narrow openings. Sometimes we will need to take into account the electric and magnetic fields that make up light. That will be something that will be covered in later subjects and lectures. And sometimes there are processes that are even on a smaller scale, which involve individual atoms and molecules, and we need quantum theory for their treatment. However, if we're just looking at the interaction of 2 or more beams of light with each other, then we can treat them quite well using wave theory. In this slide, you can see how our theory, which has started with geometrical optics, has become gradually more complete. So rays only include the information about the direction of travel. When we look at the wave theory of light, not only do we have the direction of travel, but we also need to take into account the wave number and angular frequency. We also need to look at the speed of light and the change of the wavelength once it's inside materials. If we then develop our picture using the electric and magnetic fields, we can then further look at how the speed depends on the electromagnetic properties of the material. And finally, once we get to the particle picture of light, we look at how the energy is related to frequency. However, in these next 3 lectures, we'll be looking at the wave picture. Light is an electromagnetic phenomenon. So electric and magnetic field behavior is described by Maxwell's equations. One solution of Maxwell's equations is the wave equation, which you'll be familiar with from first year, in one dimension at least. We'll be considering more than one dimension here. One solution of the wave equation, and there are many, is the plane wave. This is certainly one of the simplest and most pragmatic. It's also called the sine wave solution. It's written in this form here, which perhaps you're unfamiliar with, but it can also be written as E naught, the amplitude, by cos k dot r minus omega t. However, cosines, trigonometric functions are a pain when it comes to integrating them or multiplying them, so we're going to use this e to the I version, the complex version instead. The k here is the wave vector, so that includes the wave number, that's the magnitude, but also the direction of propagation. And perpendicular to the direction of propagation are the wave fronts. These wave fronts are planes, hence the name. The wave vector is dotted with the position vector r, and that's simply a shorthand of writing x, y, z. Angular frequency is given by omega. Now time and position are separable, so what that means is we can, for example, sit in a fixed position r, and we can watch the wave go past us. And what we'll notice is that that little particle that we're sitting on is going to go up and down as time goes along in a simple harmonic motion. And we can do the same thing by taking a snapshot, as it were. So we're going to view the wave at fixed time and have a look at it are going along the x direction, for example. And what we'll see is that some of the particles are at their maximum displacement, some are at their maximum negative displacement, and some haven't moved at all. So that distance in x is going to give us the wavelength. That period, oops, that's actually half a wavelength that I've indicated there, and the time from it to go up and down and up again is going to give us the period. These two things, the periodicity and the wavelength, are connected by the speed. In this case, it's actually called the phase velocity. So just to let you know, some textbooks actually will include e to the I phi, the phase constant, in the amplitude, giving it a complex amplitude. So you multiply that by e to the I k dot r minus omega t, and away you go. I will actually write it out generally more explicitly, so I'll keep it having a real amplitude, and I will include that phase constant minus omega t plus phi in the complex term. K and omega can also be complex, but more on that in another subject. Watch out in the resources that you look at, the sign for omega. We're going to use e to the minus I omega t. Some people, such as engineers, for reasons known only to themselves, use e to the j omega t. As far as I can tell, that just describes a wave going backwards, so we won't use that. Now, the electric field in visible light oscillates incredibly rapidly at a rate of hundreds of terahertz. So we won't realistically see that electric field oscillating. What we will see is a time average. Now, if you want to find out about how power is flowing with a wave, well, we've already seen in first year that with mechanical waves, the intensity is proportional to the square of the amplitude. And the same result follows for the electromagnetic waves. So the energy, or the rate of energy being transported over a certain area, is going to have units of watts per meter squared. So that is the irradiance that we'll be working out. Now, there are going to be some constants in here. However, for the purposes of the interference patterns and the like that we're looking at in this lecture, we will be ignoring those because we're only interested in relative changes in intensity. So in the graph down the bottom, you can see here I have the electric field oscillating with time. Now I've squared it, so you can see how the instantaneous intensity is varying with time. And of course, we need to take the time average. We don't see that rapid oscillation. And the average of this function taken over a long time is, as you can imagine, between 0 and 1, the average is a half. If you want to formally work it out, or work it out for any other complicated waveform, then you'd use this expression on the right. When two sets of waves are made to cross each other, then we'll see some really interesting and complicated effects, and that's what we're going to be spending the rest of this lecture discussing. So the very simple law can actually be used to explain these effects. It's called the principle of superposition. It states that the resultant displacement at any point is just the sum of the displacements due to each wave completely separately. So the waves don't actually affect each other. The amplitude, frequency, and so forth of those waves remains, of those individual waves remains unchanged. So we are simply going to sum what happens at a point or even across a space as a result of the displacements from those two or more waves. How do we choose those waves? We are going to be dealing with plane waves in detail. The maths is easiest. Not only that, but any other wave can actually be described as a sum of a set of plane waves. So there's got great practical importance as well. And you can use a Fourier synthesis to create any type of wave that you like from a sum of plane waves. That's something we'll return to later in the course. When we see two or more beams acting at once and we see a variation or a modification of the intensity, we say that we are seeing an interference effect. It's a fundamental phenomenon of wave optics. However, because of the very short wavelength of light, it hasn't been recognized for most of history. Nevertheless, now that especially manufacturing has come along and these short distances are something that we can easily create in factories and laboratories, interference has become quite important. We use it both for analysis of materials, such as finding the thicknesses of thin films, or for working out the wavelength of light. And we also use it in devices. For example, the anti-reflection coatings on glasses and camera lenses is based on the interference effect, and filters and even fabrication now of computer chips is done also using interference. Now we're going to work out what happens when we have two plane waves present in the same space. We'll make a few simplifying assumptions as we go along. We're going to assume that these waves have the same polarization. We're also going to assume that they're only traveling in one dimension, so we'll let that be the x direction here. Now, according to the superposition principle, the total electric field is simply going to be the sum of the electric fields from each of the waves. So there's electric field from one wave, electric field from the other. That in itself is not exciting. The exciting stuff comes when we start looking at the intensity. The intensity is proportional, or as we're saying here, equal to the square of the electric field. Because the electric field is complex, to square it, we need to multiply it by its complex conjugate. In this case, the complex conjugate simply means that we add a negative sign in front of the I. We're also going to be assuming that the electric fields, the wave vector, and omega are all real. Okay, so we expanded out. It looks complicated, but all we've done is we've simply expanded out this multiplication in the usual way. And then what we do is we apply Euler's formula. And so you can see, let's look at these terms. Our first term here, you can see that these E's cancel out, which just leaves us with this term here. So that term is essentially going to be the intensity of the first field. And of course, we have this term here, which becomes the intensity of the second field. And then we've got the two cross terms. And those two cross terms become this thing here, which I've used Euler's formula to re-express as a cosine. So now let's take the time average, the thing that we are going to see. If we assume that these waves have exactly the same frequency, then this term here is going to go to 0. So what that means is that there is no longer a time dependence in the irradiance pattern. So you can see that time does not occur inside the cosine. So there is going to be a pattern, but it's going to be stationary. If, on the other hand, these frequencies are different, so we have different wavelengths of light, then this time term does not disappear. And so it will be oscillating in time where at whatever that difference frequency is. Now, that difference frequency is going to be incredibly fast. We won't see it. And what we see, of course, is the time average. And if you take the time average of a cosine, then the time average is equal to 0. So if our frequencies are not the same, we don't see any particular interesting pattern. But if the frequencies are the same, then we see something interesting. So we have the situation where only if the frequencies of those two interfering waves are the same will we see a cosine oscillation or a pattern in the intensity that we see. If the frequencies are different, then we can't see a pattern. Now, in this simple case where the waves are only allowed to travel along the x-axis, we can either have the situation where they're co-propagating, so we have K1 is equal to K2. They're both going in, let's say, the positive x direction. In that case, then this term here will go to 0. And what we're left with is cosine of the difference in the phase constants. So there's no pattern, as it were. Just you can tweak these phase constants if you want, but what you will just see is that your whole field will either be bright, or it will be dark, or it will be intermediate in intensity. If, on the other hand, we have K1 is equal to minus K2, so they are counter-propagating, then this term becomes 2kx. And so that means that we have this cosine oscillation in the x direction. So the oscillation in intensity is the interference pattern, and the period is going to be half a wavelength. So let's have another look at with our two interfering waves. They're traveling both in the x direction. So there's K1, you can draw in the wave fronts for that. And we have K2, which might be going the same direction or a different direction, and the wave fronts are going like that. Let's see what happens. So if they are counter-propagating, going in the opposite directions, then we see a standing wave pattern in the x direction. So the intensity, as we move in the x direction, goes bright and then dark, and then bright and then dark. And then we call these patterns fringes. If we have the situation where K1 is equal to K2, so they're co-propagating, they're going in the same direction, then we have the cosine oscillation term simply becomes cos of the difference between the phase constants. There's no variation in x, so that means that the intensity will simply be a constant across the field like that. Now let's see what happens if we play around with those phase constants. So let's take the situation where we've now got a difference between those phase constants of 1/3 of a wavelength. or perhaps better units to use would be radians, so that would be 0.3 by 2 pi radians. So first, again, we'll look at the counterpropagating situation, and you'll see that we do have bright and dark fringes as before. However, they are not as bright as before. They've also shifted a little bit in position. However, the spacing is still the same, isn't it? If we look at the situation where they are co-propagating, then we will have this constant value of intensity like this. Again, it's less bright than it was before. So for simplicity's sake, I've called the argument of that cosine delta. Okay, so that's the phase that's inside the cosine. And we know from the properties of a cosine that that is going to be a maximum when it's either 0, 2 pi, or 4 pi. So if I substitute in for 2kx in here, then you can see whenever we have a situation such that that expression is equal to 0, 2 pi, or 4 pi, we're going to have a maximum in the intensity. Also, we'll have a minimum in the intensity when this cos argument or phase is equal to pi, 3 pi, or 5 pi. So often you'll see it written in a shorthand, 0, 2 pi, 4 pi is equal to 2m times pi, where m can be 0, plus or minus 1, plus or minus 2. I'm now going to write our interference expression here slightly differently. So instead of E1 squared, I'm going to write I1. Instead of E2 squared, I'm going to write I2. And here is our interference term. Sorry, E1, E2 by cos delta, our interference term. This will take a maximum when the cos goes to 1, so that gives us a maximum of 2E1, E2, and the minimum is going to be minus 2E1, E2. So sometimes you'll see this term here written as 2 times the square root of I1, I2. In this graph here, I'm showing as a function of position the intensity. The intensity here, the average intensity, is going to be I1 plus I2. So if there were no interference taking place, then that intensity would be actually what you see, I1 plus I2. But when there's interference taking place, we see an oscillation around that mean value, and the amplitude of this oscillation is 2E1, E2. If we want to maximize the visibility of the fringes, so we want the bright fringes to be as bright as possible and the dark to be as dark as possible, then we need to increase the visibility, which is done by maximizing our function for visibility. So we increase our amplitude and decrease the mean value, and that is found by setting the magnitudes of the electric fields to be equal. So if we have electric fields that are close in magnitude, we'll have very easily seen fringes, whereas if the electric fields are quite different from each other, then our intensity pattern will be a very small wiggle on top of a relatively large constant intensity, and it will be hard to see those fringes. So let's have a look at some of the things that we've learned about interference, even though we've been dealing with calculations that involve so many assumptions. So for the two patterns, for the standing interference pattern, we had to have counterpropagation. If we wanted to simply see a constant intensity, and we could vary that using the phase constants, then we needed copropagation of our waves. To make the interference pattern as visible as possible, then we need to use similar magnitudes of electric field. We also need to have the same polarization, although that's something that we've simply assumed to be the case. The waves also need to be the same frequency. So if omega 1 is not equal to omega 2, you don't have this standing pattern. Some fun things can happen if they're slightly different, but we'll talk about that later. Finally, we need to be able to have this constant, well-defined phase difference between the waves, and that means our waves need to be coherent. If light is incoherent, then the intensity that we see when we mix two light beams is simply going to be the sum of their intensities. If we have interference taking place, then we get the extra interference term. And coherence is necessary for this to occur. So our two sources don't necessarily need to be in phase with each other. They could be shifted, and there can be a phase difference between them, but it has to remain constant. So coherence is the situation, we call it, when the phase difference between two times or places is constant. Now, a source produces light that's going to be a mix of these wave trains. So if we sort of sit in a fixed spot, such as here, the wave fronts that come past us are going to look sinusoidal for a certain time, but then there'll be changes in phase, usually quite abrupt. So the distance over which the light wave oscillates in a regular, predictable way is called the coherence length. And the time interval that it takes for this length to go past us at a fixed point is the coherence time. Now, this diagram of the wavefronts also shows us something else. If you look at these two positions that are indicated here, you can see that the behavior of the wave at these 2 points is actually correlated. So, although they're not in phase with each other, the phase relationship between these 2 points remains constant. This indicates that our light source is showing spatial coherence. Coherence is important if we want to be able to see interference. If light is incoherent, then the phase of the cosine in the interference term becomes a random function of time. And in that case, the interference pattern is going to randomly shift around at a rapid rate. It's going to average it out and make it impractical to observe. So if we want to see an interference pattern, we need to use a light source that emits coherent waves, such as from a laser or some atomic defects. Or we need to do something to our incoherent light source, such as a candle or sunlight or a lamp. Now, in the case of something like a lamp, it emits a train of waves for about 10 nanoseconds or something, and then abruptly and randomly changes phase. So it means that if we have two lamps, then the relative phase of them is only going to be constant for about 10 nanoseconds or so. So that means our interference pattern is going to be very short-lived and we won't really detect it. The way around it is to take just one lamp and to split it up so that it becomes secondary sources and then interfere those secondary sources because they've come from the same either photon relaxation or wave train, depending which picture you prefer, they will be coherent and you will see the interference pattern. In general, we will see some degree of coherence, partial coherence in our light sources. Now, a lot of the things that we'll see in coherence comes from the fact that light has bandwidth associated with it. So even in a laser, it may have a bandwidth of something like a nanometer or so, whereas white light, it might have a bandwidth of microns. So let's have a look at what happens when we superimpose a number of frequencies or wavelengths together. Now imagine we have a light source that is emitting light at two frequencies, omega 1 and omega 2. Also, because of the nature of the emission of these two frequencies, let's say that these are going to be incoherent because the creation of one frequency was an event that had nothing to do with the creation of the other frequency. So if we want to see interference from a single source, we'll have to split the light up into secondary sources which are coherent with each other so that they can interfere. So we'll see interference from the electric field at frequency omega 1, and we'll split up omega 2 and we'll see an interference pattern there. So down the bottom here you can see I have shown the interference, the standing wave pattern, when you have counter-propagating waves at omega 1 and omega 2. If you look closely, you'll see that at this particular position, both of those interference patterns see a maximum, and they both see a minimum at the same position as well. So in this part, we will see maximum contrast in our standing wave interference pattern. If we move along a while though to a certain position such as in the middle here, you'll see that because the spacing of the two patterns is different, then one pattern has gone dark, has no intensity, and the other's bright. So that means if all we're doing is measuring intensity with our detector, we'll see just something that's halfway in between, and we will see basically no contrast. Then as we move further away from that position in X, we will see the max contrast again. So what we will see then is a bright, dark region, which has high contrast, then goes to zero contrast, then goes to contrast again. And you can see that the envelope of this is the envelope that you associate with beats. We were able to add these two intensities because remember that if total intensity is equal to the intensity 1, in this case due to omega 1, plus the intensity due to omega 2, we can do that if they are incoherent with each other. If, on the other hand, by using a different light source, if we had omega 1 and omega 2 actually being coherent with each other, we'd see something different. You'll remember in the interference term we have omega 1 minus omega 2 times t inside that cosine. So in that case, you will see a cosine oscillation in the interference pattern as a function of time. In other words, you'll see a flashing, and that flashing will go on at the difference frequency. However, in the case of something like the doublet in a sodium lamp, where we have two frequencies which are emitted independently of each other, so they are incoherent with each other, we can interfere 588.995 with itself, 589.5924 with itself to get two interference patterns. And as we move our screen, look at the position of the standing interference pattern, you'll see a beating effect. So in the middle here, the contrast goes to 0, but the intensity is still finite. We've already seen that the coherence length is a measure of the distance over which a wave is nicely sinusoidal and you can predict the phase. And the time over which it is sinusoidal is the coherence time. Now the new idea is that those finite times introduce a broadening to the frequency components, delta f, delta omega, or alternatively to the wavelength components. We talk about the spectral bandwidth, delta lambda. This relationship is akin to the Heisenberg uncertainty principle. We can either talk about the width of the packet in k space times the width in x space or real space being of the order of 1 or greater, or alternatively we can talk about it in frequency and time. Either way, you can see that if we have a wave train that has a short coherence time, that will lead to an increase in the frequency bandwidth. Again, with a short coherence length, you'll see an increase in delta k, and at the same time an increase in the spectral bandwidth, delta lambda. So on the right hand side, I've illustrated a wave train which has a coherence length of LC indicated here. And you can see that that finite coherence length has resulted in a finite bandwidth, delta lambda, in the spectrum. Now in this case, this spectrum can be decomposed into 3 peaks, and we've then simulated the wave trains of those 3 peaks on the right hand side in the middle graph. You can see, well, perhaps you can't, but I hope that you can see that at the center at x is equal to 0, then these these interference patterns that we would see are all nicely lined up, and we'll see a lovely high contrast pattern there. But just as in the case where we had 2 frequencies and we were looking at beating, the further we move away from x is equal to 0, the more that we simply get a blurring out because they're all in different phases, and we end up in these regions here, low visibility fringes, and we can't see them. So this shows clearly that the finite coherence length leads to a limit in the number of fringes that you can see, which corresponds to a bandwidth, an increase in the bandwidth. So these 3 ideas of coherence length, limited number of fringes, and bandwidth are going to be related in the experiments that you carry out using white light. At the risk of sounding simplistic, I do wish to remind you of the fact that when we have waves traveling in a material that has a refractive index that's not equal to 1, the wavelength is going to be shortened compared to free space because they are slowing down. So we will have a short wavelength and we will have a larger wave number. I need to introduce this idea of optical thickness now. And that is where it is easier sometimes to compare different thicknesses of materials when you also include the refractive index with them, because that, in a sense, is including the fact that the wavelength has changed due to refractive index. Anyway, we'll see that being used shortly. Interferometers are instruments which can create and measure interference patterns. There are three principal measurements they can do. One is analysis of the wavelengths and spectral content of light. Another is distances and even displacements in terms of wavelengths of light. And a third is measurements of refractive index. Often in interferometers, we're not so much concerned with the entire cosine oscillation as simply the positions where the fringes are maxima and minima. In that case, we're interested mostly in the phase of the cosine. So this phase, as we know, is a function of k, where k is 2 pi on lambda. And it's also a function of any differences in distance. In this case, we have to talk about the optical thickness rather than actual thickness, and that will give us a phase constant. Now this will reach a maximum when it's equal to 2 pi times m, and m is equal to 0, plus or minus 1, plus or minus 2, and so forth. So we can use m as an integer to label each fringe. In the laboratory, you'll often have to do a measurement of some kind as a function of m. It'll be your task to work out what function of that measurement you need to plot on the y-axis in order to get a linear relationship between m and that measurement. Furthermore, if you count more and more orders, you'll find that your fit will actually improve in accuracy. Although you'll find if you go too far, then things may go a little bit unstable. We're going to be looking at two ways of describing interferometers, and today's lecture is going to consider amplitude splitting interferometers. In this case, if we can consider a light ray coming in and hitting a semi-reflective interface, some of the light will be transmitted and some of it will be reflected. Because these two waves came from the one wave, they can be recombined and produce an interference pattern because they're coherent. The other way of making an interferometer, and we'll consider this more next week, is by splitting the wavefront. So if we consider a wavefront that has sufficient spatial coherence, we can place in front of it an aperture of some sort so that we can pick off two parts of the wavefront, here and here. And because they come from the same wavefront, these will be coherent with each other and they can interfere. There are other ways of classifying interferometers, and you can read more about these in the text or lab notes as relevant. This really simple interferometer is a thin film. We have light from a single source. It travels down to the thin film. It's reflected from both the front interface, we'll call that ray 1, and the back interface, we'll call that ray 2. These are coherent rays, so they will interfere. They're coherent because they came from the same original wave train, that is, as long as this extra distance that's travelled by ray 2 is going to be less than the coherence length. These are also co-propagating rays. That means that we won't see a standing fringe pattern. we will just see a uniform brightness, and how bright that is going to depend on the phase constants. So we have co-propagating waves, so in the interference term, that x dependence goes to 0, and we just have to work out what happens to these phase constants. The optical path difference is what we're going to use to work out what those phase differences work out to be. Ray 2 travels a distance of 2d in a refractive medium of n, so the distance it travels, or its optical path difference, is 2nd. Now ray 1, on the other hand, it hasn't travelled any distance. Remember, we're only considering what happens when they interfere just above this surface. Ray 1 hasn't travelled any distance, however, it's reflected off a medium that has a higher refractive index than the incident medium. So it's undergone a phase shift of half a wavelength. So if we multiply the optical path difference by 2 pi on lambda, that gives us our phase difference. And I've inserted this into the interference term expression down here. In this simulation in the top left, I'm showing what would happen if you could increase the thickness of the film. If we start at 0 thickness and we increase it, you'll see that originally the reflected light that we are detecting is going to be absent, it will be dark. But then our film will appear bright. As it increases the thickness, it will become dark again and then bright, and so forth. We can look at another dependence. This time, how does the brightness of that reflected light depend on wavelength? As you can see in this simulation, at some wavelengths we will have constructive interference, and so the film will appear quite bright at those wavelengths, whereas at other wavelengths we have destructive interference, and that light is not going to be detected at all. And this is actually the principle behind anti-reflection coatings, such as on your glasses or your camera lenses or so forth. The idea is that you have a thin film of a certain refractive index and thickness so that you can decrease the reflectance at a desired wavelength, and that's going to stop haziness caused by internally sort of reflected light, and it's going to improve the image brightness. Let's have a look at the previous situation in a bit more detail. Our interferometer consists of the source, the thin film, and the light detector. We can measure either in reflection or transmission. And in this case, when we want to have a look at the spectral content of the light, a light detector is a spectrometer, so it measures intensity as a function of wavelength. We'll keep the model here general, so light is not necessarily incident only normally. It could come in at any angle theta, and we have to include then cos theta in our optical path length. The thing with doing spectral measurements is we can't access the entire spectral range, and these maxima don't come labelled. They don't have a sign above them that says m is equal to 1 or 59 or whatever. We don't know what order we have, so m itself is unknown. What we do know is that between two successive maxima or minima, the difference in the order, delta m, has to be 1. So we then just need to rearrange this expression in order to get m1 minus m2, or indeed mn minus mn plus 1. And then we don't actually have to know what the orders are, only the difference between them. That expression then gives us ND, the optical path length, in terms of the difference in M, the angle of incidence theta, and the difference in the inverse wavelengths at which those maxima or minima occur. Notice that interference can't actually separate out the N, the refractive index, and the D. So this is a straightforward problem. We've got a thin film. It's measured normal incidence or near normal incidence in the visible wavelength range. We've found in the visible wavelength range 3 reflection maxima at 400, 480, and 600 nanometers. So your task then is to find the optical thickness of the film, and you'll do that by considering, you can either consider these pairs where delta M is equal to 1, or if you want to, you can also try this pair here where delta M is equal to 2. We've seen that we can change interference by changing thickness and by changing wavelength. Now we're going to see how changing angle can help us to see different interference patterns. A really cool device that uses this principle is the Fabry-Perot interferometer, or the Fabry-Perot etalon. We'll see how this is different to the thin films we've been considering previously. It is a thin cavity as before, however the surfaces are quite reflective. The thickness of this cavity, the distance across it D, is actually quite large as well. It's now millimeters to centimeters rather than fraction of a millimeter, which we were considering earlier. Our light source now is going to be a point source or even an array of point sources. Point sources can emit light in all angles, so now we need to consider the angle at which the light rays are arriving at the cavity. If this angle theta is such that the light is constructively interfering, then the lens is going to focus that light to a bright spot. We also have another ray with that same angle on the other side, and that will also be focused by the lens to a bright spot. However, our system is circularly symmetric. So if we look in the focal plane of the lens, then instead of seeing just 2 bright spots, we will see a whole circle. And this results because all of those rays are incident on the cavity at the angle theta, and that circle has uniform irradiance. Another important difference is that the Fabry-Perot etalon has these highly reflective surfaces. It means that light spends a lot longer inside the cavity, bouncing around. That means we have not 2, but many beams, which are going to be contributing to the interference patterns. We have a situation called multi-beam interference. When we derived our expression before, we were only considering 2 beams, and that gave us the cosine oscillation in the interference pattern. With the multi-beam interference, we still have to satisfy the condition that the phase is equal to 2 pi m for a maximum, so the maximum is still going to appear in the same positions. However, the profile is different now. It's much narrower. From the point of view of someone who's interested in examining and analyzing the wavelength components of a light source, this is really good because the wavelengths are going to be much easier to resolve. So the Fabry-Perot interferometer is all about getting good wavelength resolution. The wavelength resolution we can talk about as being the difference between 2 wavelengths that we can see, and we want this to be really small. If we take this expression here and we differentiate with respect to wavelength, we'll get this expression, and we can see that in order to reduce this delta lambda, that is to improve our resolution, we want to increase the denominator, which we're going to do by increasing d. So that's why our d is so large. The disadvantage is that if d is so large, then the orders m are going to be very big. We're going to see lots and lots of orders, and they're going to be, as you can see in the picture on the left, separated by very small angles, so they're a little bit hard to resolve. This is not that hard to fix experimentally. We need to increase the focal length of the lens so that we can view the pattern a long distance from the lens and improve the resolution that way. We can build a telescope system if we're so inclined. Now then, if we use this approximate expression then for the difference in angle that we can measure, then we can write an expression that gives us a linear relationship between the change in order and the change in angle squared, and we will have a linear relationship in order to extremely accurately work out our wavelength. One of the most important types of interferometers is the Michelson interferometer. We have a source of light, and the light from it is split into two, so I'll use two different colors to follow those beams. One light beam is transmitted through a beam splitter, reflects off a mirror. It returns to the beam splitter, and a fraction of that is then reflected down to the detector. The other wave that we will consider travels from the source to the beam splitter, but that is going to be reflected towards the mirror. Now that light is going to head back towards the beam splitter, and some of it is transmitted through to the detector. So the interference is going to come about because there is a path difference, and that path difference is created by moving one of these mirrors backwards and forwards. As the mirror is moved a distance d, then the path difference that's experienced by the blue ray is going to change by a distance 2d. Now these are co-propagating waves, so we are not going to see the stationary interference pattern. But what we do is we change this distance of the mirror, and in that way we change the interference condition that we have at the detector, so it moves from constructive to destructive to constructive interference and so forth. So we can work out the wavelength quite easily by shifting the mirror at distance d, and let's call this delta m to make it clearer, counting the number of fringes, and that will give us the wavelength quite quickly. Now if we look at just the change of one fringe, we can see that the mirror only needs to move by half a wavelength, which is a very short distance. So we do need to be clever using gearing or something to move that mirror very accurately. We can use white light fringes to work out where our equal path lengths are located. So this is d is equal to 0 here. Our Michelson interferometers are used for spectral analysis, looking at, for example, transforming the spectrum from an infrared into a interferogram like this, and we can work out the spectral content that way. We can also look at very small changes in N, and we can look at very small changes in D, and might be fun if you go and read something about LIGO and their recent successes. There are a whole lot of interference fringes where the optical thickness, ND, is the dominant parameter. And these are called lateral fringes, and that's because they are the patterns are right angles to the direction that light is traveling. They're also called fringes of equal thickness. Now, just as before, when we were looking at our thin films, we have light incident normally. Some of it was reflecting off the top surface, and some of it was transmitted through the top surface and reflected off the back surface, and these rays were interfering. Now, however, we have a thickness that varies as a function of position. So let's say in this wedge, we have a bright fringe, a maximum at position x1 and another one at position x2. We can say something about the increase in the thickness of the material there. That change in thickness, delta D, has to be equal to the wavelength in the material divided by 2. And because the wavelength in the material is equal to the wavelength in vacuum divided by the refractive index, we can re-express this as the adjacent fringes corresponding to a change in optical thickness, ND, is equal to the wavelength in free space divided by 2. So we're going to see these interference fringes, and they're kind of like contour lines on a topographic map. Each fringe is going to show you all the points in that film where the optical thickness ND is a constant. Now, in general, the refractive index doesn't actually vary, so the fringes will then correspond to regions of equal thickness. And they can actually be really useful for looking at surface features in optical elements, because they'll be able to detect changes in thickness of the order of half the wavelength. So it might be that we have a simple wedge where the thickness is increasing linearly with x, and so we'll see a nice interference pattern like this. However, if we have a more complicated surface, instead of a wedge, let's say we put, we rest a spherical surface on top of a flat surface, and now this is our cavity in here, then you can see that that is going to be a nonlinear function with position x. And in the laboratory, you'll be carrying out this experiment to see if you can find those rings, observe them, and make measurements in order to calculate what is the radius of curvature of that spherical surface. Now, in this situation, we have, it's an air cavity, so we have n is equal to 1. And sometimes when we're looking at thin films, we don't know the refractive index, so we can't make an absolute measurement of D. We have a measurement generally of ND. So either we need to have a reference thickness measurement at some point, or alternatively we can use more than one wavelength, and then we can solve the equation simultaneously in order to find out what D is.